I want to thank the organizer for this invitation and the opportunity to present our work in such, first of all, nice conference, but also such a very nice place. I'm really impressed. And so it's really a great pleasure to be here. And before I start my presentation, I would like to mention that, of course, all the results I will show in this talk would have been possible with a fruitful collaboration with our friends and collaborators and colleagues whose names are just writing here, and I'd like to acknowledge them before I talk. So obviously, the keywords of my project, my work, the work I will present here, are antiferromagnets, but also multiferroics. And I hope that by the end of the talk, I will convince you that a multiferroic system can be also quite interesting for our problem, our issues. So after the very impressive talk of Davide, I guess I absolutely don't need to talk about nickel oxide anymore. And so I will jump directly to the second slide, because of course we are also interested in these antiferromagnetic materials for various properties and obviously for all the terrestrial capabilities and the fact they can be manipulated on the picosecond timescales. And with this question, beside all the very nice fundamental physics open questions, there is one natural question, which is what role could they play in future ultrafast devices? And asking this question, there are obviously two challenges with these antiferromagnets that they have to be mentioned and tackled. These obviously they are quite difficult to manipulate and to control because of this lack of magnetization, and they're also quite difficult to observe and their distribution and their dynamics, and especially if they are in infinite epitaxial layers. This is where my second keywords enter into play, because besides a lot of tricks, the tricks we are using and we are choosing is to consider what we call multiferroic materials. So multiferroic materials are these materials which possess different kind of ferric order. So obviously the one we're going to be interested in are magnetic and antiferromagnetic, but they can be also coupled to other kind of ferric order, such as ferroelectricity or some kind of elastic order, mechanical order. And considering these materials, the material of choice is, of course, bismuth ferrite, because it is both ferroelectric and antiferromagnetic materials at room temperature, in quite high temperature. And if we consider this, because this, what I forgot to mention is that these ferric order are not only present in these materials, but they're also coupled together. That means that we can think of using an electric field to control the antiferromagnetic order, or a magnetic field to control the electric order, etc., etc. But obviously, using an electric field to control the antiferromagnetic order would be quite an advantage. So coming back to bismuth ferrite, that we can call BFO, it has this kind of perovskite structures, and with the ferroelectricity, the polarization, the ferroelectric polarization, which can line along all the 1-1-1 direction. And we have to mention that there is a quite large magneto-electric coupling, and the first consequence of this very large magneto-electric coupling is what we call this antiferromagnetic cycloid. So it's an antiferromagnet, but then it wants to curl and to wind in a chiral way, and this is because of this magneto-electric coupling. But the nice things about that materials is that, as I said, we can control, or we can the antiferromagnetic order is somehow coupled to the ferric order, and this, for example, you can see that in an experiment we did. So here it's a piezo response force microscope. So basically what you see here, this is basically the image of the ferroelectric order. And then we write a square where we have only one polarization, and here it is NV center image. These are done in Montpellier, in the group of Saint-Jacques, and these were done at the UMR-CNRS Thales. And here you can nicely see the cycloid. And if you decide to write in the other direction, you see that the cycloid has changed its propagation direction, basically its winding direction. So it's a kind of nice proof of this magneto-electric coupling, the fact that one is locked to the other. The other very nice thing about these materials is that depending on which kind of substrate you grow it, then you can have some strain, because there is an epitaxial mix match. And with the strain engineering, you can have all kinds of different antiferromagnetic order. For example, here you can see, again, you have the ferroelectricity, and here you can see some kind of cycloid. So you have the normal kind of cycloid, what we call the type 1, but we can have also another kind of cycloid, the type 2. I will not enter into the detail of this because it's not the goal of my talk, but in some cases, you can destabilize the cycloid into a G-type antiferromagnet. So that means that playing with the strain engineering, you can really have a very nice zoology of different kind of antiferromagnetic order that you can kind of control. And so to sum up about this system, so it's definitely a quite rich playground for electric control of the antiferromagnetic order on one place, but also what we have to mention is that in this bismuth ferrite, it has also a quite high frequency, as you will see by the end of the talk, but it is known that basically it has antiferromagnetic resonances around 600 gigahertz, something like this. So on the other hand, it's kind of a complex, textures. So here is the sample with which we're going to play today. It's typically a thin layer of 100 nanometers grown on the STO substrate. And what you can see here, again, these are PFM images, so the only thing you have to know is that basically represent the ferritic domains. Here you can have the 8 possible variants like this, and these are quite small. And choosing the STO, we choose to be in the G-type kind of antiferromagnet, okay? And for each polarization, P polarization, you can have 3 different kind of S domain, basically. These are the equivalent of the S domain. So altogether, that makes an interesting system because we have another level to handle the antiferromagnetic order, but it's a quite complex system. And for this, we have to choose a system or a technique to be able to investigate it. And we have chosen, among some others, a nonlinear process, actually the lowest order, which is second harmonic generation. And the principle is quite easy. It's basically you shine light at omega on the system, and under certain circumstances, it can regenerate or re-emit light at twice the frequency, second harmonic generation. And I said that at the leading order, this process is only allowed in the system which shows some kind of breaking of inversion symmetry. And speaking of, it's quite interesting because naturally speaking, ferroelectricity breaks the inversion symmetry. And what you have to know, there is another thing. If you break the time inversion symmetry, then you can have access to some extent to some kind of magnetic order. So that could be a nice tool to investigate it. And as a proof, I want to mention the pioneer work of basically of Manfred Fibig, where they managed to image, for example, some pure chromium oxide, where you can definitely see, so it's in the flop states, you can definitely see very nicely in a crystal the different antiferromagnetic domains. With some tricks, you can even see some 180 domains, so from here to here, which might be quite difficult, but you can even see it. And in this very nice paper, they image exactly our problem, which is, because in this case, it's another multiferric, it's the manganite, and they managed to decouple the image of the ferroelectric domains and the image, basically, of the antiferromagnetic domains. So we enter the game, but as you have seen at the beginning, the electric structure is quite small, and as we are using an optical technique, we are limited by the diffraction. So the first thing we wanted to do is to increase and to do that in a single ferroelectric domain. And this is possible, as I already mentioned, if you use this PFM and then you apply a voltage, you are able to write a large single ferroelectric domains. So basically, here, already for the problem I mentioned at the beginning, how can we control all the multitude of antiferromagnetic domains, the multiple T domain, multiple S domain. Here, basically, you reduce already the possibility of T domains from 12 to 1, basically. From 4 to 1, and basically, you reduce the problem of the S domain for the antiferromagnetic domain from 12 to 3. So basically, we are able to write this single domain. So we do these experiments. So basically, we do a wide field experiment. So we shine the light on the sample, and then we collect the light in a CCD camera. So I spare you all the technical details. So our laser, it's a kilohertz laser, about 90 femtoseconds. In this case, the light was at 900 nanometers. And these are the kind of raw image that we have. Then you can definitely see, this is for different kind of polarization direction. So basically, you can directly see the square we have written, but at some different polarization direction, you can see that there is a substructures. And if you do a bit more of analysis, you can note that if you do for a single pixel a full angular dependence, you can note, and a bit of symmetry, then you can note that in each pixel, you have two contributions. You have one gray contribution, which is the contribution basically which is only for the ferroelectricity. It's normal, you are in a single ferroelectric domain. And you have a tiny contribution which changes sign from places to places. And by reconstructing this asymmetry, basically, we are able to image the antiferromagnetic domains. So I spare you the detail, but basically we have two contributions. One contribution which is only the ferroelectricity, and one which is basically the ferroelectricity times the antiferromagnetism, and it's in a single antiferromagnetic domain, then it becomes the antiferromagnetic vectors. So here it is what we can do. But we can do even a bit more, because what we have to note is that electric fields are also breaking the symmetry. And it has been shown, for example, that we can image this electric field. So to illustrate this, this is a little experiment we have done in our lab. So here, these are interdigital fingers on the, basically it's on the BTO. We are not expecting to see anything for second harmonic generation. We put a voltage between these fingers. So at 0 voltage, we see nothing. And at 40 voltage, suddenly you see some second harmonic generation appearing. This is basically the contribution of what we call the electric field-induced second harmonic generation. People have even done that to measure terahertz field. So it's a very nice technique. So in our BFO, of course, things are becoming a bit more complicated because then we have to add all this antiferromagnetic part. But nonetheless, okay, I will skip this one. But basically, if you do a bit of tensor geometry, you can see in the BFO point group, you can see if you apply an electric field along X, Y, or Z, what's going to be the contribution. And if you do this, you can see that, for example, an electric field along the Y direction will mostly tilt our angular dependence, while some other will change the ratio between the two configurations of incoming polarization, et cetera, et cetera. And something we wanted to note is, for example, if you look at these edges, it seems that we have lost some kind of long or big red domains, antiferromagnetic domains. And what you have to know is when we have written this with the PFM, we were not fully aligned along the 110 direction. And the ferritic polarization will lie anywhere along this 110 direction. It's locked on the crystallographic axis, okay? And by just rotating it a bit, then you create some electrical charging on the sides. And so this is basically a white field, and you note, as with my little demonstration, that we have this kind of small rotation. And if you, for example, report this small dependence here, you see that on the edges, then it clearly appears that we have this small contribution. Forget about this, because this is only true for the analysis in the single ferroelectric domains. So then you see, for example, with our technique, we can see that we have antiferromagnetic domain, we are able to image them, and we can even see this locking with the electric field. Of course, we've tried several other things. We've tried to heat up the samples close to the Curie temperature, to nail temperature, to see if it's changing. We have switched the polarizations from places to places, and we see that even in some cases, we managed to generate large single antiferromagnetic domains. That was not so easy to do and to reproduce, so we are still working on this to really fully understand what happened here. And something which is interesting here is what we have done. We have reapplied locally an electric field with the tip of this PFM by increasing the electric field and noticing at what voltage we are changing the antiferromagnetic contribution, and at a very small voltage, we're already changing it. What is very interesting here is a subcoercive change of antiferromagnetic domain. So that means we don't only need to move the polarization, we can only apply the small electric field. This is what is interesting. But the last thing is that actually what we've noticed is by increasing quite a lot the intensity of the light, we have changed all the pattern of the antiferromagnetic domains. And if we did that while we are applying the very, very intense light, then we can even see that the angular dependence was fully changing. What we are thinking is that, well, of course, bismuth ferrite it generates second harmonic generation because it breaks the central symmetry, okay, the inversion symmetry. And if it does that, not only you can do the second harmonic generation, but you can do this evil twin, which is optical rectification. Optical rectification is basically generating a small transient polarization while the light is on, basically. And this is what we think and what happened while changing completely the antiferromagnetic domains. And at that stage, we were here, and so we said, no, we really need to dig into the dynamics, and so we moved to time-resolve second harmonic generation to try to investigate and image this contribution. So this is what we have done. And basically, the setup the configuration is the following. So we still have our probe, which is a second harmonic generation at 900 nanometers. But then we bring a pump at 800 nanometers. And with the idea of, we said that we want to use this more transient polarization to trigger dynamics and to see if we can do something with it. And this is what we've done. And so what we are doing, basically, we are taking snapshot at some delay. So the pump was focused the pump was focused here on basically 10 microns. I forgot to say it's a 10 micron square, but here. And then we do that as we sweep the delay line. And like this, we are able to get basically a snapshot of the time evolution of the second harmonic signal. As we do this, we can, of course, do this kind of different image where at negative time, where there is no excitation, where at negative time, when there is no excitation, the red and blue, you can just say that it's a different kind of antiferromagnetic domains. And of course, you can see that this is evolving with time, and then when we are around T0, we can see a large evolution, and this is what we are trying to investigate. But to do this, basically, what we will do, we will go to each kind of domains, and we will try to trace the time evolution of the second harmonic signal. And the nice thing about this is that by doing this, we can really identify a family of antiferromagnetic domains and trace and track the time evolution of the dynamics. And of course, here we can see two kinds of things. The first thing, we can see what's happening after the excitation, and we can note two things. We can note first the onset of an oscillation, which is at about 600 gigahertz. I will 600 and 700 gigahertz. What we can think of being the electromagnon in the bismuth ferrite. And if you go at 45 and 135 degree, where basically the magnetism is the most active in our signal, we see this decay of about 1 picosecond, which is the signature of the ultra-fast demagnetization in this process. And then the second thing, of course, is seeing what's happening when basically we are around the T0, where we try to basically understand if we can image this kind of transient polarization. With the idea, as I said, when the pump is on, then we have this transient polarization, and we add a small contribution, and we come back to what I told you at the beginning about this electric field-induced second harmonic generation. If you do that, you can look at how the angular dependence evolves and try to understand it. And it's not so easy, because there are many contributions, but if we would want to be convinced about the fact that optical rectification might be the process which is playing the main role. Of course, I will not ask you to look at the detail of this image, but this is depending on the pump polarization. If you go on one direction or the other direction, etc., and you can clearly see that there is a pump polarization direction dependence. So that put the fingers on the fact that it's maybe the polarization which is induced by optical rectification. And actually, you can also follow basically how it evolves with how the angular dependence evolved with time, and you can see a clear change if you, for example, look at the pump polarization which is at 45 degree and the one which is 135 degree. So basically, this is where we are now, and this is where we're trying to understand. It's unfinished work. And what we'd like to try to see is, can we have some insight about this more transient polarization? And this is what we're trying to do. And for example, with the small model or calculation that I've presented you, for example, we can differentiate two things, either if the polarization is rotating like this, the small p polarization, or if we add a small electric field like that. And you can see, for example, in one case, one is just breathing for the second harmonic angular dependence, and the other is the ratio between 90 degree and 30 degree is changing. And as we can see here, at around T0, you have a huge change in this asymmetry, which pointing out that we certainly have a huge electric field which is generated perpendicular to the layer. Sorry. Of course, we did some check also, because as we are shining quite a huge amount of light, I forgot to say it's about 40 millijoule per square centimeter. Then we have checked the change in transition, because we are going through the whole structures. It's about 10%. So of course it plays a role, but it cannot explain all what we have seen here, especially the change in the angular dependence. So in the last minutes, I still have 5 minutes. Okay. So I represent another unfinished work but because then I wanted to share where we are, maybe, and we have a lot of questions, so maybe you can help me with understanding. The problem is, of course, imaging very small domains if you are in a thin epitaxial layers, okay? And recently, basically, we want to move from far-field imaging to near-field imaging. So we have acquired basically a SNOM, an aperture SNOM, and the principle is the following. You shine light on a metallic tip, and the electric field is enhanced at the apex of the tip. And basically, what's happening here is like if you had a nano lamp, okay, that you rest a scanner around the sample. And this tip also acts as something which scatters the near-field light, then you can collect. So this is the idea. It's the very beginning, and the idea, of course, okay, came because there is also this very nice work in the group of Marcus Raschke. So here it's only the ferroelectricity, where they managed to image very small ferroelectric domains using second harmonic generation in thin layer of this manganite. So we have built up this setup, and basically, I will go quickly here. So basically, this is the kind of image we can get from second harmonic generation. It's very fresh. It's maybe a month old, something like this. And obviously, it does not look exactly as a little reminder as the structure we had at the beginning. So we have a lot of things to understand, and this is basically where we are right now. And with this, I come to my conclusion. And basically, the message I wanted to address today is that, of course, multiferroic could be a nice and rich playground for antiferromagnetic materials or antiferromagnetic dynamic studies in general, because it gives us another handle with the electric field. And electric fields are not so complicated to apply, and if we manage to master it, we can maybe control easily the antiferromagnetic contribution. So as you have seen, we need some kind of tool, and also put a lot of focus on our technique, which is second harmonic generation. And basically, we managed to visualize this kind of domain, and also we are trying now to see more with electrical control, trying to see how we can stabilize a long domain with some kind of switching, ferroelectric switching. And basically the last message I wanted to address is we need to be able to address this excitation. So with our technique, we managed to see it, and now we're trying to master it and to control it. And with this, I thank you for your attention.
Okay, thank you very much. Now we have time for questions.